How's it going? So, something crazy happened on the last stream, and that was Grok. I asked Grok to code an AI model. But here's the thing is I don't have any experience with AI development. I barely have experience with Python. And it was able to generate an entire new model from scratch, which is crazy because this is something that normally you would need a PhD in order to make. So what I want to do is show you how I did that. And then hopefully we can walk through it together. And the other thing I want to show is the added advantage of AI, which is that you can take something like this that you really want to learn. Everyone's talking about vibe coding, but what I think is really incredible is vibe learning. So once we have an example, we can break it down and we can really dive into what we have questions on. So yeah, with that, what I'm going to do is create a new chat. So here's the question. Can AI create AI? Can I have a Grok create the code for a new AI model? Let's check it out. Okay, so here's the prompt that I gave it. Please create a code for a basic neural network that can identify images 0 through 9. This is the most basic project you can do. Use PyTorch and provide an explanation for each step with a final code output at the bottom. Let's send that off and see what it can do. All right, so let's create a new project and see if we can run it. We'll create a new project called Simple Neural Network in this window. While that's spinning up, let's look at each of these steps. Sorry, reading the comments right now. Yep, am reading it right now. Those comments look very AI generated. Yeah, so the whole test right here is, can I use AI to create an entire AI model? And Then what I want to do is actually go through and learn from that. So for each of these steps, we're going to break down the code, but then we're also going to um, take that and learn from it. So dive into each step and ask it, okay, for step 1, can you explain why you, I mean, of course, libraries just make sense, but here we go. Let's create a new Python file. Let's paste that and see where we have errors. So we've got a few things we need to import. I don't think that'll actually work because torch needs to be PyTorch. But yeah, I don't think that's gonna work. So what I'm gonna do is you just boot up the terminal. Yeah, I'm probably gonna have to pip install. So let's open up a terminal. We'll make it even just so it all matches on the screen. Here we go. Okay, cool. So this is just to see if AI can actually just output an entire thing. And I think the answer is yes. Let's go to the PyTorch documentation. Honestly, let me see if I can just look at previous stuff. I think I can. I think it was just this one. Pip install torch vision. Cool. Ow. Hold on. Got a baby sleeping back there, so we're working on borrowed time right now. Cool. So got that. Let's just go ahead and run it and see if anything breaks. Okay, cool. So it's going through the training epochs. You can see pretty bad accuracy on the first one, way better on the second. Let's wait for it to do all 5 of these. Yeah, a little bit better. We'll see what the final accuracy is. Okay. Cool. So the final accuracy is 96.82%, which is crazy considering I did nothing. But let's see what that looks like. So what I'm going to do next is ask Grok to actually output accuracy. please output Okay, so what we're going to do next is add an extra little like matplotlib. So an extra display that shows incorrect examples. And I prompted it wrong because it's trying to do all of them. Give me 1 second though, because she's screaming. So check this out here. Yeah. Something like this. Boom. This is how you code while a baby is asleep. All right, so if she cries again, I'm just gonna throw her in here, but let's see. So, and feel free to have any, throw any comments or inputs in the chat. I'm happy to answer those. Let's just copy this whole thing and just paste the updated version. And it looks like we need to import matplotlib. Okay, so we're waiting on that package to install. You can see it in the bottom. Should be good now. It's actually kind of helpful to have this camera right here. All right. Back to coding. Okay. Boom. Switch to the bounce ball and we're back in business. Okay. So here we go. We got Grok here. And it has printed a new one. We threw it in here. We imported the new library. Let's run this. Okay, so you can see on this first training cycle, 39% wrong, 20% wrong, So it's kind of cut its loss in half. 14%, so marginally better. You can kind of see that over time the loss is getting better, but not by a ton. Loss 11. And then we can expect about a 4. Okay, so yeah, 96.56. And check this out. So here are the correctly classified images. So you can see what the actual answer is. And this is the data set that it was trained on. So you can see handwritten images. And then for each of these images, the predicted one was the same number as what the true answer was. So it was able to look at this and say, that's a 7, that's a 2, that's a 1, 0, and 4, right? And then I think if we close out of this, it will open up the incorrectly classified images, which it's funny how, like, that's a 5, that's crazy. You know, it's a 6, which honestly, I would have no idea. I would say 9 or something, you know? Here's what else it said. Here are some of the other ones that it got wrong. So it thought this was a 6 instead of a 5. I probably would too. It predicted a 4 for this one, which debatable. It's funny because this is actually how like Germans kind of make their 1 look. Imagine vibe coding. Yeah, I'm giving it a try. For things that I don't really have the ability to do, what I really want to get into is like vibe coding, but then also on top of that, not just vibe coding, but vibe learning behind it. So that's what I'm hoping to do by the end of the stream, is have like a pretty solid understanding of why each of these lines of code are what they're doing and why they're doing it. So the true value is 2, the predicted value is 4. That one makes a little less sense. True value is 9, predicted value is 8. Yeah, I would guess that's a G. And then the true value is 4, the predicted value is 6. I guess. That one, I don't think I would have had a problem with. I would have thought it's more 4-ish than anything else. Cool. So that is the model. And here's what's incredible about that though is, right, like this is something that I've talked with PhD students about them building, right? This is not something that's accessible to normal people. But with AI, we can quickly start building things and playing with them and learn from the top level down, right? We can play with it, and instead of having to understand everything from the bottom up, we can play around with it and work from the top down. And I think that's incredible, especially for learning. So what I want to do is actually, my goal is to learn this, learn all of this code, and then by the end of the day, try to replicate it from scratch. So let's give that a try. I'll say here are some I'll just see what it says if I do this. And I'm trying to start as easy as possible, as accessible as possible, and then we'll dial in what we really need. But really, this is step 1. We're looking at, they define the transformer. And it looks like that's a normalization. So is this the actual model? I don't think so. Nope. So this is something I definitely want an explanation on. I want to see where they're getting this data set from, where they're putting it. And then of course there's the loader and the tester. So I just want it to explain to me. And what we're doing, I like to call it VibeLEARNIng. So that's funny because its step one is different than the code step one. So, one sec. All right, sorry about that. So here's what we're doing. Let's break down each of these. So we built our first neural net. Let's go ahead and break down step one, which is all these imports. So here are all the imports for step one. Let's look at each of them. Torch, this is PyTorch. So this is the PyTorch library. And this is how you're going to be building the models. One thing I want to do in the future is figure out how to set up GPU CUDA compatibility, but I don't have that yet. So then torch.nn is also something that they import. Okay. Simple neural network. It's a subclass of an NN model. Okay, cool. Torch Optim as Optim. Okay, so this is algorithms. Oh yeah, like the Atom Optimizer. Okay. So that's the optimizers. And then Torch Vision, that's where we're getting our data set and our transformers. Okay, so the transformer is what pre-processes images. Okay, and then the last import, if we look at this, utils data import data loader. That's loading data in batches. And then of course matplotlib is just to show the images. So honestly, I can just rerun this so I can show you how the model performed. Okay, so step 2 is to load the data set, train the data set, and then train the loader, or at least create a training and a testing loader. So let's break this down. So for the code to set up the transform, chains multiple data pre-processing into a single pipeline. Here we apply 2 transformations to each MSIT image, converting it to a tensor and normalizing picture values. So cool. So here's what our model was able to do. I just make this a little smaller. Cool. So here's the code that we're looking at, and we're having it break it down. Okay. So transform to tensor, which is this line right here. Converts the images or NumPy array into PyTorch tensors. Okay, so this is just pre-processing all of the images, taking all of the ranges, because if you think about each pixel here, it's going to be grayscale, so 0 through 255 for brightness. And what it does, it takes that and it changes, it just shrinks it down to 0 through 1. So basically divides by 255, but that gives it standardization and makes the math, I'm sure, a little easier. Let's see why. So for this line, neural networks and PyTorch operate on tensors, not raw images. This transformation ensures the data input is in the format model it can process. For MNIST, each 28 by 28 grayscale image becomes a tensor shape 1 by 28 by 28. One channel for grayscale, height, and width. So I'm going to dive deeper into this just so I understand it. The conversion reshapes the image and scales pixel values by dividing it by 255, for example. So then what I want to ask is, let me make sure I'm understanding this properly. For transform to tensor, Is it turning performing this? Okay. For each pixel, okay, yeah, I understand division. The images are 28 by 28 grayscale one channel with pixel values 0 to 55. Processes all 784 pixels individually. Gotcha. Okay. Each an integer in 0 to 255 to a float in 0 to 1. This scaling is crucial. How is the output stored? PyTorch tensor, a multidimensional array optimized for numerical computations. Number of channels, height, width. Okay. So this is the value. This is the height and the width. So then each element in the tensor is a floating point number. After it transforms to tensor. Yeah, okay, that makes sense, but so it is a vector. Roll in the pipeline. Gosh. So it's saying these are the dimensions. Or this is the shape, so 1 by 28 by 28 for each tensor. Stored in memory by CPU default, grouped batches. Okay. Okay, cool. So I'm feeling good on that. Transform to tensor. And then the normalization with a mean and a standard deviation is basically just normalize it. So this is all pre-processing the data. Let's go back to the explanation. So here we go. Trained data set is what we're moving on to next. So these lines right here. So let's look at what these lines of code are doing so we can better understand it. These lines load the MSINT data set, which is 60,000 training images and 10,000 test images of handwritten digits 0 through 9, each 28 by 28. So here's the parameters. Root data specifies the directory where the data set is stored. So what this is doing is it's loading this data set, which is already pre-configured in PyTorch, and it's putting it in the root of my project in data. So if we go here, root, there's a new data folder, and you can see all of the images are in here. Cool. Training is true. So it's important to separate your training from your testing. And that's done with this Boolean right here. Training is true, training is false. Let's check out download. So download is equal to true. If the files aren't found in the project already, then they'll be downloaded. And finally, the transform is equal to transform. Little tautology for you. But what that's doing is that's defining the transform as the transform that we defined right here. So we create the transform and then we set the transform in our data set and in our testing data. And then finally, we create the data loaders. So let's look at these two lines of code right here. All right, so these next two lines, what we're doing is training a data loader and a testing loader. So let's see what this says. The data loader wraps the data and provides many batches of data, enabling efficient training and testing. It handles batching, shuffling, and parallel data loading. So what it's doing is it's really just optimizing the training, making sure that the model is being effectively trained. The data set that's being loaded is either going to be the training one or the testing one. Batch size is equal to 64. That specifies that each batch contains 64 images and their corresponding labels. This balances memory usage and training speed. So does that mean that each epoch, that would be my first question. Is each epoch okay. So cool. So to better understand the data loader, what I want to do is kind of ask just a few more questions. So if not, how I'd like to see, okay, so let's keep going through this. If there's more questions, we'll write it down. Train data set, batch size is equal to 64. Shuffle is true. And for this one, shuffle is false. So I'm assuming the reason we're shuffling this data set is so it doesn't just get trained on like ones in an entire batch. But there's that randomness would account for a better training distribution. Let's go ahead and see. That'll be another question we'll ask. Okay, and then finally, let's just read off the final amount. Training on the entire data set, 60,000 images at once, is infeasible. That makes sense. So what you do is you batch it and you give it just what it needs to start learning. Data loader yields batches of shape, batch size, channels, height, width. So if you think of each of these as a dimension, yeah, so we're computing in 4 dimensions right now. It's the batch size, which is the number of images. It's the value, which we've transformed it to be 0 through 1. But then it's also the height and the width of each of the images. So each of those image has a height and a width. So a 2-dimensional image with a variable value with a batch size of 64. So we have 64 image values, 64 pixel values, and 28 by 28 pixels per image. Okay, let's see why this is essential. Data preparation. So enables mini batch handling, which is critical for scalability, training scalability. It also supports parallel loading, which speeds up data preparation, especially on multi-core system. Oh, okay. So that actually is interesting because yeah, parallel loading would be, this is a bad example. People are gonna roast me for this, but in my mind, it's kind of like a genetic algorithm when you see people play a video game over and over and it's got all the little Marios running across the stage or whatever. You can run all of them in parallel and learn from the best. And then of course we split training and testing, so we're not studying the answers to the test before we take it. Okay, cool. Okay, so that's something I want to learn in the future, is how to create custom data sets. Let's just add that as a comment. Okay, cool. So let's move on. I'm gonna have it answer these questions that I typed up from the last section, and then we'll move on to the next one. And again, like I said, my goal would be that by the end of this like vibe learning session, I'm actually able to reproduce this code and like explain the whole thing from start to finish. Okay. Okay, so let's just see this. Does not use a single batch of data, instead an epoch, and follows processing the entire training data set, which is divided into multiple smaller batches. Data loader handles this division automatically. Okay. 938 each epoch, 938 branches, 937. During the loop, during the training, the loop iterates over all the batches in the training loader for each epoch. Significance of the batches. Okay. So I kind of understand this. Um, but I think when we get into the code, this will kind of be explained. So I think for now, I'm going to keep moving forward. So really, the batches just help it get an accurate estimation, but then also vectorize all of that and backprop, like train the model to be a little bit better without having to really chunk the whole thing all at once. So it just I'm assuming what it does is it iteratively improves it instead of having to calculate 60,000 vectors all at once and then learn from that. Mini batch gradient descent, balancing memory, computational speed, gradient stability. Okay. Yeah, yeah. So that's it. They allow the model to improve incrementally, um, in lieu of insane hardware. Okay, cool. And then my second question I had is, why is the training data? So the second question I had is, why is the training data set shuffled while the testing data set is not? Okay, so with this data set, if it weren't shuffled, then it would train on all the zeros, all the ones, all the twos, all the threes, right? So there's an order bias that comes with that. But by shuffling it, we get 64 scrambled images that it can train off of for the next batch. So it allows us to train the model without having to worry about introducing extra biases. And then, so it looks like the next thing is why. So that's why we do have that shuffled, but then why do we not shuffle this one? The reason is because we want the testing to be reproducible. We want to be able to generate the same test and evaluation at the end. So by not shuffling this, it actually gives us the ability to kind of standardize the testing. Also, since we're running through it, it's not as big of an issue because we're testing the model, not training it. So the bias isn't really much of a factor. So that's where we're at with that. Let's keep going for a little bit. So for those of you that just joined, I'll kind of give you the background. We built a little AI model. You can see how it's performed right here. But then over time, what we did is we actually, I call it like VibeLEARNIng, but we're driving through each of the steps in the code step by step and kind of breaking down what they do. And the intent for this is that maybe not today, but by tomorrow, hopefully I understand all of this and I can, if not reproduce the code, I can at least understand all of it, but hopefully reproduce all of it. With a good understanding of how to make a basic AI neural network. And the cool thing about that is this is kind of the foundation of all artificial intelligence stuff. So with that, the next thing we're going to move on to is step 2, which is to actually define the simple neural network. And my kid is going or is screaming, so I'm actually going to end it today. But thanks so much for watching, everyone. I'll see you hopefully tomorrow.